Hey, it's Dr. J. I'm back. Today we're going to talk more about limits and particular continuity. So we'll call this video Continuity Part 2. In Part 1 of this video, we were focused on one particular point. And so I gave the definition of what it means to be continuous at a point. In this video, we're concerned with continuity on an interval. And in fact, we want to find the largest possible interval on which a function is continuous. So in the definition of continuity so far, we gave the definition as being continuous at a point. So next we'll give the definition of continuous on an interval. And the definition is so obvious. It's almost a waste of space to write the interval, to write the definition of continuous on an interval down. It's a very obvious and quite intuitive definition. A function is continuous on an interval if it's continuous at every value of x in the interval. So when we talk about intervals of continuity, we're talking about values of x. And more important than this definition I forgot how to spell theorem. Theorem, right? Yeah. Is a theorem that's much more important than the definition. It's actually specific to particular functions that we're going to be talking about. I will give this theorem without proof. The proof of this is beyond the scope of the course, but it becomes rather obvious when I start doing the examples. Polynomial, rational, exponential, power, and logarithmic functions are continuous on their domains. I'll just say domains. I mean the whole thing. Running out of space. So again, our goal is to find the largest possible interval where a function is continuous. To be continuous on an interval means that you have to be continuous at every value within the interval. And these 5 different types of functions, which are the most common functions we will see in this course, are continuous on their entire domains. Now, they don't all have the same domain. So you take a polynomial function, you take its domain, and then that will answer this question. So in other words, the answer to the question, what's the largest possible interval on which a function is continuous, is equivalent to the question, what is the domain? Which makes it pretty straightforward how we're going to answer the question. Let's see an example. Find the domain of the function. All right. Well, this is a polynomial function. Polynomial function, the domain is negative infinity to infinity. In other words, all real numbers. So a function is continuous on an interval. This is what we mean by an interval. This is a type of interval. The intervals might get a little bit more complicated as we move along. In fact, they will. So that's the domain. So f is continuous on the same interval, negative infinity to infinity. So it is equivalent. To find the domain is equivalent to finding the largest possible interval on which the function is continuous. Polynomials are the easiest ones. I should also mention this includes constant functions and linear functions. Both of these are special cases of polynomials. A constant function is a polynomial of degree 0. A linear function is a polynomial of degree 1. We've seen examples of both of those in the last video. This is a polynomial of degree 2. So polynomials of any degree are continuous on the entire number line, all real numbers. There are no discontinuities. So that's about as long as that is going to last. It's about to get much harder. Other functions. Rational, exponential, power functions. Power functions include square roots. I'll explain what we mean by that in a second. And logarithms are not always going to be so easy. So what are some restrictions on domain? You probably remember this from algebra. If not, here's a quick review. Restrictions on domain. These are numbers that cannot be included in the domain. We exclude any value of x that causes division by 0 So anytime we have a value of x that causes division by 0, we must exclude that value. An even root of a negative number most of the time it's a square root in this course, but we might see some other roots that are not square, like fourth roots or sixth roots. So even roots of a negative number. And then the logarithm of a non-positive number. So you cannot take the logarithm of a number that's non-positive. Non-positive means negative or possibly zero. Why not just say negative or zero? Well, we could. Yeah, we could say that. So those are the three domain restrictions. Example one is a polynomial. It's probably the most pure, simple function that we've seen and that we will see, and it has a domain of all real numbers, no restrictions. In all of these questions, I will be finding the largest possible interval. I sometimes phrase it differently, but I want you to know that this means the same thing. And sometimes there's more than one interval. So find the largest possible interval or intervals on which the function is continuous. How about something like that? So this is a rational function. It's the ratio of two polynomials. We must exclude any value of x that causes the denominator to be 0. Division by 0. So we exclude any number that causes the denominator to be 0. Very quick calculation will tell you that x cannot be negative 8. We call this an excluded value. So the domain is the set of all x such that x is not equal to negative 8 as an interval we say negative infinity to negative 8, open parenthesis means not including negative 8, union negative 8 to infinity. We're talking about intervals, so I'm writing these as a union. It's the U of two distinct or disjoint intervals. And again, the theorem says the function will be continuous on its entire domain. So this is not only the domain of the function, but it's also the largest interval on which the function is continuous. All right, moving right along. Not too shabby. This is really just algebra, just a review of algebra, and in particular applying algebra to the concept of continuity. I guess if you go back to what we were talking about in part 1, it would mean that the function is discontinuous at negative 8, right? That would be where it's not continuous. So everything except negative 8 is where it is continuous. I should mention, since I'm kind of summarizing not just continuity, but everything we've really learned in chapter 1, this means that there is an asymptote, a vertical asymptote at negative 8. It could possibly be a hole, So at this point, I should say it's either a whole or an asymptote. To determine that, I would have to take a limit. I'm not going to do that in this video because I'm focused primarily on continuity and I've answered the question. If you could simplify this and take the limit as x approaches -8 and you get a finite number, a real number, then it would be a whole, be a removable discontinuity. Or if you can't do that, then it would be an asymptote. I believe this one is in fact an asymptote. But we know that either way, it's an excluded value. It cannot be part of the domain. And so it cannot be part of the interval of continuity. Okay, the next rule that we talk about, we're going to talk about all of these today, but this next I'm kind of going in order, an even root. So this is an even root. The index is 2. In the old days, we used to actually write a little 2 right there. You still sometimes see that. You know, when I broke out my cell phone calculator, I noticed that even the cell phone calculators, even though they're rather modern, uses sort of an old-fashioned notation for square roots. Most textbooks don't. I don't think our textbook uses the index. In fact, I know it doesn't. I read it this morning. So it's an invisible index of 2, so that's an even root, and we typically don't write it unless you want to. It's implied to be 2. All right, so we must exclude any value that makes this negative. So we exclude any value that makes this negative. So this is what we're excluding. Well, that means we are including the opposite of that. Let's go ahead and write that. I like to use different color. So this rule tells us what we're excluding. We're excluding anything that makes the radicand or the inside of the radical negative. So we're excluding negatives. So that means we're including everything that's greater than or equal to 0. The domain is what you're actually including, not what you're excluding. So in the last example, I found the exclusion, and then I said the domain is everything except that, right? That's a useful way to do it when there's only one or possibly 2 numbers that you're excluding, a small number of numbers. In this one, we're excluding a whole bunch of numbers, right? I'll come back to this theorem in a minute. So let's go ahead and solve this. And just for fun, I'll solve them both. So I'm adding -4 to both sides, or also known as subtracting. And then I'm dividing by -12. And you remember your algebra. When you divide by a negative, you reverse. You simplify that, and you get -4 divided by -12 is 1/3. So x is less than or equal to 1/3. If I would have solved this, I would have got x is greater than 1/3. So x is greater than 1/3 is what we're excluding. Sometimes call that throwing out. We're excluding it. X is less than or equal to 1/3 is what we're going to keep in the domain. So you don't really have to do both of these. I just want to make sure that the language is very clear. You can either find the exclusion and then throw that part out, or you can find the inclusion and then just keep everything that's in the inclusion. So the domain is the set of all x such that x is less than or equal to 1/3 as an interval that's -infinity to 1/3 with a square bracket. And so by the theorem, this is the largest possible interval on which the function is continuous. If you go outside of that interval, it will not be continuous. This is the largest possible interval. Okay. So before I erase this, just wanted to clarify a couple things. I normally don't find the exclusion for a square root. I just go straight to the inclusion. So I sort of have a different technique, but I wanted to show you both ways. I also don't always reverse the inequality. Sometimes the inequality will stay greater than. The only reason why it switched to less than or equal to was because we divided by a negative. So keep that in mind. If this 12 had been a positive 12, then it would be greater than or equal to 1/3. I would not have reversed it. So I just want to point that out now before we get too far down the road. Okay. I do want you to know both methods, though. I don't always use both methods, but you should know how to find the exclusions. So find the values for which the function is discontinuous. In other words, find the values of x where the function is not continuous. Use the results to find the domain. So that's kind of like both of what I just did. First, tell me where it's not continuous, and then tell me what the domain is. So we've got f of x. All right. So, where is the function discontinuous? So, discontinuous, we take this and we set it not equal to 0. Now, you can either solve this by brute force. You can use brute force, meaning just force it to tell you what x is by using some formula or some machinery or something. I like to use a more elegant approach. I like to try factoring first. If factoring doesn't work, then I'll resort to brute force, which would be like some algebraic manipulation, you know, dividing everybody by 2, or, you know, completing the square, or putting it into a formula like the quadratic formula. If I get really desperate, I might use some software, you know, some program that tells me how to solve it. I rarely do that unless it's, you know, I just have no other option. Sometimes refer to that as the nuclear option, when nothing else will work, use a machine. I like to exercise some of the previous algebra that I've demonstrated. So I'm looking at the leading term. It's 2x times x would be 2x squared. For the moment, I'm going to ignore the middle term. Ignore that middle term. And just look at the last term, 54. How about 9 and 6? All right. And the reason why I'm ignoring the middle is I don't know if it's going to equal 21 or not. Let's see. Oh, negative 21. So then I hope that I can get negative 21 out of this. Well, 2 times negative 6 would be negative 12x. And then negative 9 times x would be negative 9x. And when I add them, they should add to be the middle term. So this is my mental check. It does, in fact, check out. If this doesn't add to be the middle term, then I would try something besides 9 and 6. I could just switch them, 6 and 9, same numbers. I could use totally different numbers. I could do 2 and 27, I guess. Does that work? 2 and 27? Yeah, 2 and 27. I could do 3 and 18, right? But I don't have to. I got it in my first guess, 9 and 6. It's usually the most obvious thing, right? Every once in a while, you'll get one that you try the most obvious. Not by obvious, I mean like 4th or 5th grade numbers. You know, 9 times 6 is 54. I mean, that's one you've known since you were 9 years old, I hope. All right, 9 or 10, depending on when you learn this. Okay. Now, again, this is not the answer. This is the factorization. I still have a little ways to go. So I've got 2x minus 9 does not equal 0, and x minus 6 does not equal 0. Separating them with a comma. So x does not equal 9 halves. Or x does not equal 6. So those are my excluded values. I usually just write the x one time, like that. Now, I want to make something very clear, because sometimes I will ask for the domain, and sometimes I will ask for the discontinuities. Discontinuities are also known as excluded values. So that's what these are. These are the kicked out. These are the throwaway numbers. All right. Essentially, it means that they're either holes on the graph or asymptotes. We don't know yet. We'd have to do a little more work to figure that out, which we may have to, but not in this problem. Okay, now once you have that, you can use the results to find the domain. I don't need this mental math anymore. The domain is negative infinity to 9 halves. You do have to put them in the right order. 9 halves is less than 6. union 9/2 to 6, union 6 to infinity. So there's your domain. All of these are parentheses. You only use the square bracket if it's a greater than or equal to, or a less than or equal to. But not in this example. In this example, they're all not equal to. Not equal to essentially means less than or greater than. I think I mentioned that earlier. When I say not equal to 0, I mean it's either greater than or it's less than, but it's not actually equal to it. It's just getting very close to that point, but not actually equaling these points. Okay, so that's the domain. It's also the largest interval on which the function is continuous. And this is the reason why we pluralize it. I guess I should say this is the largest possible set of intervals. I'm not going to really correct my English. On which f is continuous. All right, so there are 3 intervals on which x is continuous. All right. Let's try another one. Example 5. I'm starting to have some variety in this lecture. Not that it matters, but not every function will be called f for the remainder of this course. We've seen some other variables, not variables, names of functions. In terms of variables, we've really only seen x, and I think we saw t briefly showed up for one of our problems. Okay. So this is an this is an odd root. Yeah, odd root. You know, the index is 3. For odd roots, we don't expect you to see an invisible odd number. So if that's an odd number, we actually have to put it. It's normally a 3, but it could be a 3 or a 5 or a 7 or any other odd number. We don't expect you to see them without, indicating them. So there's no restriction there. No restriction. However, since it's in the denominator, we have the restriction that it can't be 0. So there's no restriction based on the index. So the index is not giving us a restriction. What's giving us a restriction is that the x squared minus 16 is in the denominator. So that means we can ignore the cube root, or the radical, and we can just say that it's not equal to 0. This one's pretty straightforward. I'm not going to spend a lot of time factoring it. It's the difference of 2 perfect squares. So it's x minus 4, x plus 4. Obviously, because 4 times 4 is 16. One of them's negative, the other one's positive, so that when you multiply a negative and a positive, you get a negative. So that's pretty basic algebra. So I'm just going to say x is not 4, x is not negative 4. I usually put them in order. So these are our excluded values. I don't care what order they're in when you solve it, but when you get to the final answer, I like to see them in order. Sometimes the computer will mark it right even when they're out of order, but sometimes it won't. It really depends on the phrasing of the question and the format of the answer. So for this particular format, it really doesn't matter. You could have gotten away with it. But when you go to the domain, and if you already have them in order, it makes it a lot easier to not get marked wrong in the domain. So the domain requires that it be in order from least to greatest, or from largest to smallest, or from negative to positive. As you go from left to right, it should be in the order in which they exist in the number line, in the graphing. This is kind of a one-dimensional viewpoint of what the graph looks like. It's telling you that the x values are either less than -4, not equal to -4, but less than -4. Or they're between -4 and +4. Or they're greater than 4. So it's kind of giving you a one-dimensional viewpoint of what the graph looks like. It doesn't really tell us what y looks like. That would be a different question entirely. So the discontinuities are the excluded values, -4 and 4. And the domain are the included values. This is the intervals on which it's continuous. This is where it's discontinuous. Again, I really think the language is just as important as the math. Included, continuous. Excluded, discontinuous. Yeah, we use these words intentionally to help guide us through the subject. Okay, one more of these, and then we'll have to move on to a different type of function. So let's do another one of these square roots. Same question, the last one. I already erased the instructions, but the same instruction. Let's find the excluded values, and let's find the domain. All right, so in this one we have two different things going on. We've got even root. So we're going to set the radicand greater than or equal to 0. And then we've got an excluded value not equal to 0. So this is an inclusion, and this is an exclusion. So in other words, when we're done with this, we're going to include all the numbers that come from x plus 5 is greater than 0, and then we're going to throw out any number that causes the denominator to be 0. All right. So let's go ahead. X plus 5 greater than or equal to 0. That's a one-step process. X is greater than or equal to -5. So that's included. All right, that's where it's continuous. X is greater than or equal to 5. And 24x minus 6 is not 0. So 24x is not equal to 6. So x is not 1/4. That's excluded. So we're saying x must be greater than or equal to -5, and it cannot be equal to 1/4. So greater than or equal to -5. It's a square bracket. Now, normally we would go all the way to infinity, right? The problem is we have to exclude the number 1/4. So we're going to go from -5 to 1/4. Then we're going to put an open parenthesis because it's been excluded. It's not equal to that. Then we're going to union these together. That's how you join together two disjoint sets. And then you say from 1/4 to infinity. And there you go. That's your domain. All right. So this is the largest interval. It's actually more than one interval on which G is continuous. I just realized in the last one I might have accidentally started calling it F halfway through the problem. It's an old habit. I always think of every function as being F, and I have to frequently remind myself, go back to the beginning and make sure you're calling it the right thing. So I'll let you correct me if necessary. I'm not sure what I said. I could just say the function. That's just a generic way to say it and keep it safe. All right, so that sort of sums it up for the different types. So remember, polynomials. Polynomials are things like, a n x to the n plus blah, blah, blah. Polynomials. So those have infinite domains, continuous everywhere. Yeah. Rational functions. Rational functions are things like what we just saw. Yeah, something like this. P of x over Q of x. And so what we do is we set the denominator not equal to 0. That's what we did here. Yeah. Then we have power functions, also known as roots. So something like, I don't know, x to the 1/2. That's the same as the square root of x. Or x to the 1/3. That would be the cube root of x. Power functions are a huge category of functions. Polynomials are a small piece of what power functions can be. Power functions are a little more complicated. The way we refer to them is typically as roots. You could argue, well, if a polynomial only has one term, then it is a type of power function. Something like that, or like that. Those are also power functions. For this lecture, I'm focusing on these two types, the square root and the cube root. I'm not sure that everybody remembers that that's true. Yeah. You can also have negative power functions. Negative 1/2, that would be 1 over the square root. And I'm getting a little bit far afield here, but I'm just sort of talking, this is what we've dealt with so far. So we've dealt with polynomials. Those are the easiest ones. Rational functions, you have to take them on a case-by-case basis. You have to set the denominator equal to 0. For these power functions, you set the inside greater than or equal to 0. Unless it's in the denominator. If it was in the denominator, you would just set it greater than 0. Yeah. And then for the odd roots, this has no restriction. Right. X can be anything. But then for this one, it's not because it's the square root, it's because it's in the denominator. You would set x not equal to 0. I should mention that when I say x, I really mean any combination of any of these functions. So you could take a polynomial and put it inside of the cube root. Or you could take a rational function and put it inside of the square root. So you can compose and combine these functions in many different ways. So these are the three that we've just looked at. All right. And we're going to see more of these as we move along. I just wanted to have them kind of all out on the board. The only one that you get a free answer for is a straight polynomial. Yeah, negative infinity to infinity. For a rational function, you should ignore the top. Yeah. Unless the top happens to be one of these. So if it is of this type. So normally you can just ignore the numerator when it's a nice polynomial function. You only care about the denominator and whether or not the denominator is equal to 0. All right, sometimes when I do these summaries, I think, oh, it's a good idea to sort of like combine all the concepts into one clean thing, but this isn't really very clean. But this is the way I see the world. You know, I see it sort of broken into these three different categories, the mathematical world. The last thing we're going to talk about when it comes to domain is exponentials and logs. Exponential functions are kind of like the polynomials of this next segment. They have domain all real numbers. All right. One of the most common bases that we see is E. Yeah, something like that. Or its cousin, its counterpart, e to the negative x. So in a previous lecture a couple days ago, you saw an entire treatment of these two types of exponential functions. So these are what are called base E. The natural base. You could have, all of these have the same domain. You could have base 2. That would also be an exponential function. I shouldn't give it the same name. Let's say something like this. It doesn't matter whether the power is negative, whether the power is positive. You can combine these together. Exponential functions, I like to think of them as almost unbreakable. Yeah, the domain is negative infinity to infinity. They don't have any breaks in them. Or they're unbroken, I guess, is another way to think about it. So all of these functions, all these exponential functions have an infinite all real number domain. However, log functions this is what we call the argument. The argument must be non-negative. Sorry. Must be positive. Not the same as non-negative. I think earlier I said it must not be non-positive. So if I say it's not non-positive, well, then it must be positive. We call that the argument. All right. Now, typically there's a base down here. It doesn't matter what the base is. Sometimes we use the letter B for base. In my next example, it's going to be a number anyway, so it doesn't matter what the base is. Now, why do I care about these two things? Well, they typically go hand in hand. So, when exponential functions show up, you get sort of a nice free answer, essentially, unbroken domain. But then very soon after exponential functions show up, their inverses are logarithms, which will also appear quite frequently moving forward. And they are not quite as nice. They must be positive. I've done a full lesson on this in algebra about how they're interrelated. The domain of an exponential is the same as the range of a log, and vice versa. The range of a exponential is the same as the domain of a log. So they are interrelated with each other. I guess the best way to see this is not in the abstract, but in an actual example. Find the domain something like this. So when I say argument, this is what I mean by the argument. So sometimes it's helpful to just use a big capital letter A here instead of the letter X, because very rarely will it just be the letter X. I mean, it could be just the letter X. That's the way we memorize logarithms, log of X. But X is often something a little bit more complicated. So this is what we call A, the argument. So the argument must be greater than 0, strictly greater than 0. All right, for all bases A, in this case, the base is 7. Which, by the way, it doesn't matter. The 7 plays no part in it. I could change the base to 9 and it would still have the same answer. I could give it no base at all. If you're just coming out of algebra last semester, you saw this towards the very end of the semester. If there's no base, it's a 10. Yeah. I'm just going to put it back to what it was, which was a 7. Okay, go ahead and solve this. Subtract 10 from both sides. divide by -2. Remember your rules of algebra. You divide it by a negative, so it's going to be x is less than 5. So there's your domain. -infinity to 5. I don't have a lot of time to get into what this means, but maybe just a brief explanation of what this means. If y equals log base 7 of 10 minus 2x, then 10 minus 2x is equal to 7 to the y. So I just want to explain what a logarithm is. If maybe you didn't take my algebra class, or maybe it's been a while since you had algebra. So when you think of a logarithmic function, you think of the base is the type of exponential that you're dealing with. But instead of having a power of x, you have a power of y. So y is the power. So when I draw my graph, I would go to 5. I'm not going to spend a lot of time breaking out the graph grid. I'm just going to very quickly explain what this means. Yeah. So, I don't know. The points probably won't be very nice, but x is less than 5, so the entire graph lies to the left of 5. I could make a little table of values. I usually do these backwards. I start with the y, and then I figure out what x is. So if y is 0, then this would be 10 minus 2x equals 7 to the 0, which is 1. I better get a number less than 5. -9. Now I'm solving now. I already know the domain. I'm just trying to get a sample point here. So I'm going to divide by -2, and sure enough, I get 4.5. So there's a dot right here, just between 4 and 5. Just in case you needed to graph something like this. Let's try one more point. You don't need very many. How about 1? Y equals 1. So now we got y equals 1. I'm really running out of room, aren't I? So y equals 1. I got 7 to the 1 equals 10 minus 2x. So 10 minus 2x equals 7. So -2x equals -3. 1.5. I'm using decimals because the logarithms typically, I mean, sometimes you get lucky and you get nice whole numbers or integers, but I mean, I'll settle for a nice decimal if it's a decent decimal. So there's 1, there's 2, there's 1.5. So x is 1.5 and y is 1. We saw graphs like this in a previous lecture, but they were flipped the other way. The asymptote was horizontal, and the graph went, either up or down. Those are the exponential functions. This is a logarithm. And so since this is the first one we've seen this semester, I just wanted to give it fair treatment. And that's what it looks like. And the reason why I wanted to show you the pictures, it is curved. I know it's kind of doesn't look that great, but it's the perspective of the camera. But it's curved just like an exponential. It's going down to negative infinity. Right? It has a vertical asymptote. And then it has the domain. So the domain should corroborate the evidence that the graph is less than 5. There is no graph over here. Yeah, this is all excluded. It's like this whole region over here just doesn't even exist. The world ends right at this dotted line here. All right, enough of that. Now you've seen it once. I'm not going to draw every logarithm that we do, but essentially they all kind of look the same. Sometimes if it was greater than 5, then it would be on the other side of the asymptote, but never both. It's always on one side or the other. All right, let's try another one. So a natural log plus a common log. This would actually have quite an interesting graph, but it would probably take me 20 minutes to draw it, so I won't. But just for some commentary, the natural log is base E. This is just commentary now. So remember the e to the x. And then the common log is base 10. 10 to the x. So if I wanted to graph this, I would have to use a combination of the two different bases. It would get pretty tricky. Let's just find the domain. All right. So what we want is we want the domain of this and the domain of this. And they're both logarithms. It doesn't matter what the base is. They both follow the same basic principle. So x must be greater than -8 and x must be greater than 6. Remember, we're talking about the x-axis here. So here's -8. So x is greater than -8. And here's 6. And means both. So both of these things must be true. So over here, x is greater than -8, but it's not greater than 6. Yeah. Over here, x is greater than 6 and it's greater than -8. So the domain is just from 6 to infinity. It's only the part in which both of these functions are true. They are both continuous in that area. One way to think about it is in this region here, only half of this function actually exists. And if only half of it exists, well, then none of it can exist. They both have to be true at the same time. Over here, to the left of -8, neither one of them exists. So this is like neither. This is like one, and then this is both. And so because we want the domain to be true, they both have to be satisfied. So it's and. It's not one or the other, but it's both. All right, I better get moving because we got a few more of these logarithms to do. That one's done. Not much else to do there. This example sets the stage for this comparison that we're going to be doing because as I move through the rest of the examples today, we're going to have to compare different domains and then choose the one that satisfies both, or maybe there's, a third option. You would have 3 of these all happening at once. Let's get on to that let's do a couple more before we get to that stage of the game. Okay, so I've got f of x is e to the negative x over log base 2 of 3x minus 11. All right. So the reason why I mentioned the exponential functions earlier is because you can just ignore them. If there's no restriction, then you can ignore it. I should be careful when I say that. If there's no restriction and it's not in the denominator and it's not inside of a square root, which is that big mess, that summary mess that I drew about how to identify a problem and whether or not you need to pay attention to it. So it's not in the denominator. It's not inside of a square root. So it's well behaved. There's no restriction. Here we actually have 2 things going on. One of them is we have the exclusion, which is that log cannot be equal to 0, right? Because it's in the denominator. Sometimes we call this the denom exclusion or the denominator exclusion or domain rule number 1, right? That was the very first rule we learned, that whenever you have a denominator, you have to exclude it. And then you have the inclusion, also known as the argument. The argument must be greater than 0. That's what we just did in the last couple examples. So I hope that's becoming clear through repetition, that when I'm looking at a denominator, I'm looking at what it's not equal to. When I'm looking at an argument, like with a square root or with a logarithm, I'm looking at what it is equal to. I'm not saying it's not equal to this. I'm saying it is equal or greater than 0. Well, let's do the inclusion first. So 3x has to be greater than 11. Divide by 3. That's not a very nice decimal, so I'm just going to leave it as a fraction, 11 thirds. If this was simplifiable, reducible, I might go a little further, but I can't. All right, I've got my denominator exclusion, so I'm trying to find out what x cannot be equal to. Yeah, that's an exclusion. Now remember, this is the reason why I made such a big deal about the logarithm a minute ago, is solving this is not easy if you don't understand the nature of a logarithm, right? Remember, this is like the y value, and you're trying to figure out the x value. So what this means there's your base. Remember the one I did, the base was 7. This time the base is 2. This is like the y value. So there's the y. And if you think about it as a graph, y is equal to 0, right? And you're trying to figure out what x is. Right? And now it becomes very easy to solve. Right? But jumping from this step to this step is very difficult if you don't understand the nature of a logarithm. Right? If you try to just solve it the way it is, it's going to be very difficult. All right? But if you translate it, you realize, oh, it's just a base 2 exponential. Watch how easy it is to solve. Anything to the 0 power is 1. Add 11 to both sides. Divide by 3. And I get x is 4. Well, I should be very careful. X is not equal to 4. I slash all my equal signs. If you write them as equal signs, that's okay while you're doing it, but make sure you remember it's an exclusion. It's not a solution. You're not saying that x is 4, you're saying that x is not 4. All right. And remember, this is a combination. So we need both to be true. So x must be greater than 11/3 and not equal to 4. All right, so it's greater than 11/3 but not equal to 4. Now, the only reason why the 4 even matters is because 11/3 is smaller than 4, right? 11/3 is like 3 2/3. If this 11/3 was larger than 4, so if this was, say, 15/3, 15/3 would be 5, yeah, then you wouldn't even have to include this because it's already not including 4. So you do have to be very careful about the location of these numbers as they appear on the line. It's not always easy with fractions to immediately understand where they're at. You got to think about it a little bit. This is 3 2/3. Or as a decimal, 3.66666, which is why I chose to just leave it as 11/3. All right, I got to move on because we only have I don't know. We've got some time left. Not as much time as I wish. But this is the end of the chapter, so we're gonna try to get through this. All right, so example 10. So now we're going to go back to what we were talking about before, which is piecewise functions. We were talking about these in the last video. This one has 3 pieces. So we have a 3-piece piecewise function. So the first thing I want to mention is what's happening at 3. All right, so that's what we call the cutoff value or the critical value. Cutoff only has 1 T. They mean the same thing. It's a critical value because it's being cut off at that value. So the first thing I want to do is figure out what's going on in that region. All right. So what's going on in that region? Is it continuous? This is kind of a replay of what we were doing in the part 1 of this video. Right? I'm just considering it at one point. And then after we answer that question, we're going to have a second question, because now we've got these other points or these other functions that may have additional points that are not necessarily the cutoff value. So there might be other critical values, right? Critical values are pretty easy to see when they're a cutoff value. I mean, it's pretty obvious, 3, right? I'm listing it out right here. All right, so let's go ahead and say the limit as x approaches 3 from the left. That left is the top piece. So that's going to be log base 5 of 3 plus 2, which is log base 5 of 5, which is 1. Right. 5 to the first power is equal to 5. Remember, logs are really just exponentials. If this was log base 5 of 25, then it would be 2, because 5 to the second power is 25, so on and so forth. All right, let's do the limit as x approaches 3 from the right. All right, from the right, greater than 3. I should mention what a -1 power means. If you haven't seen that before, you have, though. It just means it's in the denominator, and change it to a positive power. All right. It's a type of power function. The power is -1 is the power. It's also a combination or a composition of a polynomial and a power function. Right. Another name for this is a reciprocal. We have lots of different names for things. It really makes the subject interesting to be able to describe things in lots of different ways. I forgot to put the limit here. I don't want your notes to be badly written. So let's see if we can just plug in 3 squared minus 6 times 3 plus 8. 9 minus 18 plus 8. -9 plus 8. All we're looking for is if we get division by 0. We don't, so we get -1. And then finally, let's look at what f of 3 is. F of 3 is the middle row, because it's telling us x is equal to 3. That's 2 times 3, which is 6. Now, this should be screaming at you right now, right? Look, the limit on the left is equal to 1. The limit on the right is equal to -1. And the value of the function is equal to 6. That's like this. The left is here, the right is here, and the point doesn't match the left, doesn't match the right. And so, no. It is not continuous at 3. That's the definition of continuity. It's just not continuous. Well, that's pretty straightforward. That was just a review of what we did in the last one. But now we have to look at what about other critical values. Perhaps there's some other critical values out there. Are there other critical values? Well, the answer is yes. But let's just start off with we don't know. But I mean, I wouldn't be doing this example if the answer was no. I would say this example's over because there's no more critical values. We have 2 functions that have restrictions, right? The middle one is a line, which is a type of polynomial of degree 1. It doesn't have any restrictions. But we just talked about logarithms and we talked about reciprocals or rational functions. So from piece 1, we have log of x plus 2. X plus 2 must be greater than 0. So x must be greater than negative 2. All right. But this says x is less than 3. Remember, both of these things must be true. So that means piece 1 starts at negative 2 and goes to 3. This is a little bit of an abusive notation. It looks like I'm saying the coordinates negative 2, comma 3. You probably will have to get used to this if you haven't already. In algebra, this happens a lot where we use a notation that used to mean something else, and it no longer means that anymore. This means x is between negative 2 and 3. That's why it's nice to keep around our alligators or inequalities to remind us that these inequalities tell us that this piece goes between negative 2 and 3. All right. Piece 2 is just a dot or a solid point at x equals 2. All right, it was 2 comma 6. Oh man, talk about abusive behavior. This means the point 2 comma 6. This means the interval negative 2 comma 3. But if you just walked up and ran into this, on the board somewhere, and it wasn't clear that we were talking about that notation, it's misleading, right? Unfortunately, we don't have enough symbols to give everything its own notation. So we have to sometimes double dip on what we write. And it's very important that the reader understand the difference between the two. Okay, and then now going on to piece 3. Piece 3. Oh man, I'm all out of room. Maybe I can squeeze it down here. It's not a very complicated one. It's 1 over x squared minus 6x plus 8. I wrote it down earlier, but I'm writing it down again. So the denominator cannot be 0. I'm really running low here on space here. So that's going to be x minus 4, x minus 2. We've done several of these this morning, so let's just jump right to the answer. X is not 4. X is not 2. But keep in mind you're in piece number 3, which is x is greater than 3. So only this point is critical. 4. X cannot be equal to 2 because it's not in the interval. So the interval says x is greater than 3. Well, this says x is equal to 2. Well, 2 is not greater than 3, so it's not critical. It lives in another interval, so it's not critical. We can ignore it. So now, think about this. We have 3 pieces of this function. All right. We know it's not continuous at 3. We also know it's not continuous at negative 2. Right? There's an asymptote there. We also know that it's not continuous at 3. I just said that. But then what does it go? At 3, there's a dot. So there's a break in the graph. That's 3. Piece number 2 is x equals 3. I don't know why I wrote 2. All right. I wrote 2 10 minutes ago and it was the wrong number. X is equal to 3, so this is 3 comma 6. And then finally, I've got x is equal to 4. So to summarize all of this, let's do our final answer. F is continuous on the interval -2 to 3, then from 3 to 4, because x cannot equal 4, and then from 4 to infinity. Since f is defined at x equals 3, the domain only excludes the 4. That's a hell of a question. Yeah. You really have to kind of see the graph to really understand it. Let's see if I can do justice to it. Not going to be super detailed, but I'll do the best I can. So the function starts off at -2 with an asymptote. Let's see, what does it look like? It kind of looks like this. It's a log function. But then when you get to 3, there was a hole at 1. All right, so that's piece 1. And then there was a dot at 6. And then there was another hole at -1. And then when you got beyond 3, there was a graph that looked like this with another asymptote. All of that exploration kind of leads us to this graph here. And then it goes from 4 to infinity. It kind of looks like this. It's our classic reciprocal function. So this is what the graph of f looks like. So again, let's summarize this. Continuity goes from -2 to 3, and then it's discontinuous at 3. Then it goes from 3 to 4, then it's discontinuous at 4, and then it goes from 4 all the way to infinity. So this is your x-axis all the way to infinity. That's the continuity discussion. But the domain, there is a dot at x equals 3. So the domain is from -2 to 4. Goes from -2 all the way to 4. That's that piece. And then it goes from 4 to infinity. So the point of this exercise was that not every question has an immediate answer. You sometimes have to dig a little deeper. And then when you put together the two answers, they don't always agree with each other. So continuity and domain in a piecewise function can be all over the place, right? They can have lots of different results. It really depends on everything we've done in chapter 1. Most importantly, the limit and what the value of the limit is. I'm only going to have time for one more. And then, I don't know, I might post a supplemental video that shows some more detailed graphing, like how would you do this with your mouse? Maybe some additional questions, Q&A, or if you have any questions, shoot them my way before the chapter test. But this video has already gone over time, so I've got time for one more. This will be enough for you to at least get your homework done. Continue moving with the course. So I've used the term removable discontinuity quite a bit. And I don't know if it's been clear why we call it that. I have to admit, it was never quite clear to me why we use the word removable. And what we're about to do is remove the discontinuity, right? When I think of removing a discontinuity, I think of fixing the problem, right? That's the way I think of it. Or I think of patching the hole. So we have a piecewise function. It has two pieces. The top piece is when x is not equal to -6, and the bottom piece is when x is equal to -6, and k is an unknown value. And we want to make the function continuous. So before I actually do the math, let me explain what I mean. When you have something like this, it's called a hole or a removable discontinuity. Discontinuity. Yeah. I think of it as repairable, or you can patch the hole. Yeah. So I want to find exactly the right value of k. Now we're talking about x is equal to 6, so this hole exists only in one spot. -6, yeah, so it's over to the left on the graph. Again, I'm not drawing in a detailed graph here. We want to find the value of k so that when you plug in -6, it patches the hole exactly. And that's why we call it a removable discontinuity. It's not that you've removed the point, it's actually the opposite of that. You've put the point back into the hole to remove the discontinuity, thereby making the function continuous. I don't know if that's a lot to wrap your mind around, but when you remove a discontinuity, you then reinstate continuity, right? You're taking something that was broken and putting it back together, which is really the true definition of algebra. Yeah. The word algebra means to repair the broken parts, or you are obligated to fix this problem. Yeah. So you see a hole, you've got to fix it. You've got to patch the hole. Well, let's go ahead and do that. All right. This is actually, after what we just went through, a lot of the last few examples were pretty technical. This one's pretty straightforward. This one just requires the basic understanding of a limit. So the hole is going to be at -6. So let's find the limit as x approaches -6. It's a very nice, well-behaved polynomial. So we just plug in -6. All right. If it wasn't well-behaved, I might have to do some more fancy technical, factoring and canceling and multiplying and dividing. And this one's pretty straightforward. You just plug and chug. Plug in the number and pop out the answer. So I get 36 minus 60 plus 27. That's -24 plus 27, which is 3. Okay. So that means the limit is 3, which essentially means that the whole has a y value of 3. The x value is -6. So in order to patch the hole, we want to force this to be equal to 3. So we'll say 4x plus k is equal to 3. And we're not asking it to be equal to 3, right? We're telling it, you must be equal to 3. That is the only way that this hole is going to get filled. All right. Now remember, x is equal to -6, so we're actually not solving for x. X is already predetermined. So we just plug in -6, and this will tell us what k has to be. K has to be 27. Yeah. Because I ran out of board, I didn't do the math, but if you add 24 to the other side, well, this is calculus, you can do it. You're going to add it to both sides. The 24 is going to cancel. -24 is going to cancel, and you're going to get 27. And so k must be equal to 27. All right. So the limit on the left is -6. I forgot to say that, but I could say it now. The limit on the right, so the limit on the left is 3. The limit on the left as x approaches -6 is 3. Got to say it all the right way. The limit on the right as x approaches -6 is 3. So these limits agree with each other. They're both equal to 3. And then when you plug in -6, as long as this is equal to 27, then it will be continuous at that point. Well, that's the end, my friends. Until we meet again, I'm Dr. Jordan, and I'll see you on the internet.